Hello, welcome to Partial Fraction Decomposition. My name is Tuesday J. Johnson. I'm a lecturer at the University of Texas El Paso and an assistant professor at Doña Ana Community College. This is for Math 1508 Pre-Calculus at UTEP. Chapter 7, Systems of Equations and Inequalities, comes to us from Larson's 10th edition Pre-Calculus text. This is section 7.4, Partial Fractions. So let's think about what we're actually doing here. Let's look at some basics. Hopefully, you all remember how to add fractions, and if not, hit me up and I'll give a little lesson on this too. But if we have 1/2 plus 1/3, in order to add fractions, we have to have a common denominator. So we find our common denominator, which is 6. So what do I have to multiply the denominator of 2 by to make 6? I'll multiply it by 3, so I have to multiply the numerator by 3 also. What do I multiply the denominator 3 by to make 6? It's a 2, so I have to multiply the numerator by 2 also. Multiply straight across, so I'll have 3/6 plus 2/6. Once I have the same denominator, I'll add the numerators and get 5/6. We know this, or at least we've learned this at some point in time if you're taking a class that involves partial fraction decomposition. So the method of partial fraction decomposition is taking our result 5/6 and breaking it apart into its component pieces, 1/2 plus 1/3. This is one of my favorite topics in all of pre-calculus, so I'll try to tamp down my excitement, but no guarantees. Alright, so if I want to decompose a rational function, n of x over dx, into partial fractions, the first thing I'm going to do is I'm going to divide if it's improper. So if the numerator has a larger degree than the denominator, we're going to divide to obtain the polynomial, the quotient, and then the remainder will be a proper fraction. We're going to focus on the proper fraction. So we'll factor the denominator completely into linear and irreducible quadratic factors. These irreducible quadratic factors have complex zeros, so we cannot reduce them over the reals. For every linear factor in the given denominator, each power up to the one in the factorization, the partial fraction decomposition must include the following sum, so we're going to add them, of m fractions. So for every linear factor in our denominator, we have a potential constant in the numerator. But we have to list that fraction as many times as that factor appears. And we'll do some examples and make that a little more clear, but the important thing to remember here is a linear denominator always has a potential constant numerator. For all of our irreducible quadratic factors, the partial fraction decomposition must include the following sum of n of fractions. So a quadratic denominator will have a linear numerator. And it could be that b is 0, it could be that c is 0. They won't both be 0 in every case. But if there's a quadratic factor that's repeated, we have to repeat the fraction with the increasing powers as well. So a quadratic denominator has a potentially linear numerator. And we're going to find values for the a's that I had on the previous screen, the b's and the c's that I have here. So let's look at this form. If we want to write the form of the partial fraction decomposition of the rational expression, and that's it, just write the form, first step, what we're going to do is we take x minus 2 over x squared plus 4x plus 3 and completely factor the denominator. To factor this denominator, it will be x plus 3 times x plus 1. And since we have two linear factors, none of them are repeated, our form will be a, some unknown, over x plus 3, plus b over x plus 1. Each linear factor gets its own fraction. The order doesn't matter. If you chose to write a over x plus 1 and b over x plus 3, that's cool. You're going to get the correct answer, in quotes, but your a and b values will be switched because you switched the order of the fractions. It doesn't matter. Also, the linear denominator, x plus 3, has a constant numerator, so just an a. The x plus 1 is linear, 1 degree less, always proper fractions, a constant numerator. All right, so that's it for writing the form, and this is going to be the first couple of steps in our entire decomposition when we solve. So let's do a couple more examples. Given x squared minus 3x plus 2 over 4x cubed plus 11x squared, notice I don't do anything with my numerator when it comes to solving the form. In my denominator, that's all I care about. Denominator, I'm going to factor out the x squared. I'm left with 4x plus 11. And x squared does look like a quadratic, but it's not, because this has a solution over the real numbers. It's not an irreducible quadratic. Yes, it's quadratic. No, it's not irreducible. X squared is the same as x times x. It's a repeated linear factor. So since x is a factor twice, I'll have a over x and b over x squared. All right? X happens twice in our denominator, so I need two fractions for the x, first power and second power. The 4x plus 11 will also get its own fraction with c over 4x plus 11. Since x is squared, power of 2, it has to be listed twice in both powers. A few more examples we're not solving. So if we have x plus 2 to the fourth, this is a linear root, a linear factor repeated 4 times. So I have 4 fractions. Notice the x plus 2 to the first, x plus 2 squared, x plus 2 cubed, x plus 2 to the fourth. And the powers on the outside, they're just repeated linear factors. Because they're linear still, I have a constant in my numerator. Whereas in number 4, my denominator of x minus 1 times x squared plus x plus 1, this is an irreducible quadratic. X minus 1 is my linear factor. Looks like I typed this one wrong. Let's just fill in a minus sign right there. Sorry about that. It does not change, just a typo. Probably would have been easier to change that to a plus. The linear factor of x minus 1 has a constant possible numerator, and the irreducible quadratic factor of x squared plus x plus 1 has a potential linear numerator. Notice the bx plus c. Again, number 5, x times x squared minus 5x minus 4 all squared, an irreducible quadratic. A over x, linear factor, constant numerator. X squared minus 5x minus 4, potential linear numerator, irreducible quadratic. And then the second time. And notice we don't use a sub 1, b sub 1, c sub 1. I'll just use the capital letters, just make my way through the alphabet. A, B, C, D, E, as needed. Quadratic denominators always have linear numerators. Alright, so that's how we set it up. How do we solve? For any linear factors, like we had in most of the examples, we could substitute the zeros of the distinct linear factors into the basic equation. For repeated linear factors, we're going to use the coefficients determined in step 1 to rewrite the basic equation. Then we could substitute other convenient values of x and solve for what remains. Instructions very rarely make complete sense when you just read them. We need examples in order to see what happens, and that's what we're going to do next. For quadratic factors, and you can also do this for linear factors, we're going to expand the basic equation, collect terms according to the powers of x, and then equate the coefficients of like terms to obtain equations involving a, b, c, and so on, and use a system of linear equations to solve. This line right here tells us why we're in chapter 7 of this particular text, systems of equations. So we're going to use systems of equations to solve when we equate coefficients. Let's look at some examples. Alright, so write the partial fraction decomposition. That's telling us, alright, here's 5/6. I want you to rewrite it as 1/2 plus 1/3. So we need to find our values. We need to write it as a sum of fractions, a sum of rational functions. So first we're going to factor and write the form. That's what we did in our previous examples. We factor out the x. So we'll have 3 over x times x minus 3. And then I use this to write the form. I have x as a linear factor, so a over x. I have x minus 3 as a linear factor, so plus b over x minus 3. This was what we did in the first set of examples. Hopefully you're good to go. So now our steps are going to be, we're going to multiply this equation by the least common denominator. And the least common denominator, LCD, is always the original denominator. And when I multiply on the left, both my x and my x minus 3 cancel, and I'm left with a 3. When I multiply a over x times the denominator, my x's cancel. I'm left with a times x minus 3. And when I multiply b over x minus 3 times x minus 3, my x minus 3's cancel, and I'm left with b times x. Notice, in my form, a is over x, and so after I multiply by the LCD, I end up multiplying a by what was missing from the denominator, and what's missing is the x minus 3. I multiply b, the numerator, by what's missing from its denominator, and that's the x. It didn't have the x factor. So if you want to skip this step of writing it all out and canceling, you multiply by what the denominator doesn't have from the common denominator. We'll go over that again. Alright, so we have our equation. 3 equals a times x minus 3 plus bx. Using the zeros of the original common denominator, we know that when x is 0, right, we have a 0 denominator. When x is 3, we have a 0 denominator. When x is 0, I'll put 0 in everywhere I see an x in my main equation. So I'll have 3 equals a times 0 minus 3 plus b times 0. Well, that's 3 equals negative 3a. b cancels out. So a must be negative 1. When x equals 3, I'll have 3 on the left. A times 3 minus 3 plus b times 3. Everywhere I see an x, I replace it by 3. 3 minus 3 is 0, and 0 times a is 0. So I'll end up with 3 equals 3b and b equals 1. That's fantastic, but you haven't finished. Remember, we have our form, 3 over x times x minus 3, written as a over x plus b over x minus 3. Now I substitute my a value of negative 1, my b value of 1, and I like to write the form so that I get the a and the b in the correct locations after I find them. Let's do another example. X plus 1 over x squared minus x minus 6. First step, factor our denominator. Now that I have two linear factors, I make two equations. A over x minus 3 plus b over x plus 2 for this particular denominator. Second step, multiply this part of the equation. Let me put a box around it. That's what I'm looking at. I'm going to multiply that equation by x minus 3 times x plus 2. So on the left, it cancels my denominator entirely. For a over x minus 3, the x minus 3's will cancel out. I'll be left with a times x plus 2. And here I'll have b times x minus 3. The zeros of the original denominator when x equals 3. I put in 3 for x. Everywhere I see an x, I replace it with 3. Notice 3 minus 3 makes 0 times b. So I'll have a 5a equals 4 and a equals 4/5. When x is negative 2, it's another 0. When x is negative 2, everywhere I see an x, I replace it with negative 2. Everywhere I see an x, replace it with negative 2. And I do the arithmetic. Negative 2 plus 1 is negative 1. I'll have 0 a's, so a cancels out. Negative 5b, so b equals 1/5. And this is fantastic. You factor it, great job. You write the form, fantastic. Oh, remember that this equation has to hold for all x values, and if it holds for all x values, well, why not use the zeros, the things that cancel out? You found the a and b, fantastic job, but you're not done yet. You're not done yet. You actually have to write, which I forgot to do. A is 4/5, so I'll have 4/5 times x minus 3, it's a 3, plus 1/5 times x plus 2. So don't forget to actually write the answer. This is the answer. Not the form, not the a equals, not the b equals, but the actual partial fraction decomposition is your answer. Let's look at another example. 1 over 4x squared minus 9. That looks like the difference of squares to me, so I can factor it as 1 over 2x minus 3 times 2x plus 3. This is a over 2x minus 3 plus b over 2x plus 3. Remember, the order doesn't matter. When I get an a, if you wrote those in the opposite order, that would be your b value, and so on. When x equals 3 halves, right, 3 halves will make a 0 in my denominator. So 3 halves times 2, I'll end up with 6a equals 1. Notice over here, the 2's cancel. 3 minus 3 is 0. Always these, quote, easy values, the zeros of the denominators, will cancel out one of them. If 1 equals 6a, then a equals 1/6. Now I could use the negative 3 halves, the opposite of value, since this is the difference of squares. We have both positive and negative. Negative 3 halves is going to cancel out my a. 2's cancel. A negative 3 and a negative 3 makes a negative 6 times b. Still have a 1 on the left. That was my original numerator. So b equals negative 1/6. Writing my form, replacing a and b appropriately, my minus sign in the middle rather than a plus a negative 1/6. And if you prefer, you can write the 6 in the denominator. Just make sure you keep the parentheses around your linear factors. Alright, now, does that always work? Do the zeros of the denominators always work? And the answer is no, unfortunately. So if I have 6x squared minus 1 over x squared times x minus 1 squared, notice that the linear factor of x is repeated, so a over x plus b over x squared. The linear factor of x minus 1 is repeated, so I have c over x minus 1 plus d over x minus 1 all squared. When I multiply by my denominator, my original denominator, which is the least common denominator, the a is missing an x and both x minus 1's. The b over x squared is missing x minus 1 squared. The c over x minus 1 is missing both x squareds and a single x minus 1. And d over x minus 1 all squared, this fraction is missing the x squared from the original denominator, and so that's what d is multiplied by. Now, 0 is a 0 of a denominator and 1. So these are our easy values. That's what we're going to use. When x equals 0, make sure you plug it in on the left as well as the right. A times 0, that's 0. C times 0 squared, D times 0 squared. C, D, and A are going to go away. All I'm left with is 0 minus 1 all squared, which is 1. B equals negative 1. Easy answer. Love it. When x equals 1, right, all of this work exactly the same. When x equals 1, I put 1 in for x, and this is going to make a 0, this is going to make a 0, this is going to make a 0. The only place that really matters is the dx squared. And 1 squared is 1, so 6 minus 1, 5 equals d. But those are the only zeros I have for my denominators. I have no idea what a and c are, even though I know b and d. So fill in b equals negative 1. Fill in d equals 5. I could simplify a little bit, or I can leave it. I'm going to use some quote easy values to find a and c. And I've already used 0 and 1, so my next easy value is negative 1. If I put negative 1 in for x, everywhere there's an x, I'll end up with 5 equals negative 4a minus 4 minus 2c plus 5. I encourage you to pause as needed in order to make sure I'm not lying to you in that. I've checked this one so I know it's right, but make sure you know it's right. When I simplify this, I can subtract 5 from both sides and then add 4, so I have 4 equals negative 4a minus 2c. After I've used 1, 0, and negative 1, my next easy value, quote easy value, is x equals 2. When I put 2 in for x, I'll have 2 squared is 4. 6 times 4 is 24, minus 1 is 23 on the left. I encourage you to check and make sure that my right-hand side is correct. It is. And when I subtract 20 and add 1, I'll end up with 4 equals 2a plus 4c. Now we can use the results of these, quote, easy values to form a system of equations and find values for a and c. So solving the system of equations, I'm going to multiply the top equation by 2 to eliminate c. When I multiply the top equation by 2, I multiply every single term by 2. Add straight down, I get 12 equals negative 6a, so a equals negative 2. If a equals negative 2, negative 2 times 2 is negative 4. Add 4 to both sides. 8 equals 4c, so c equals a positive 2. Substituting, we know a is negative 2, so negative 2 over x. We know b is negative 1 over x squared. We know c is 2 over x minus 1, and 5 over x minus 1 all squared. It's a lot of work, but each step was easy. Each step is easy, there's just a lot of steps to remember. Now I haven't done any with quadratic, irreducible quadratics, so let's do at least one of those. When I have x squared minus 4x plus 7 over x plus 1 times x squared minus 2x plus 3, I see that I do indeed have an irreducible quadratic, two things that multiply to be 3, have the same sign, and add to be negative 2. Right? That same sign is what makes it bad for us. It's irreducible. So I have a linear factor of x plus 1. An irreducible quadratic factor, so I'll have the bx plus c in my numerator, a possible linear numerator for a quadratic denominator. When I multiply by my common denominator, my original denominator, I'll have a times this quadratic plus bx plus c times x plus 1. Rather than trying the, quote, easy values, let's use the method of equating coefficients. So what I'm going to do is I'm going to multiply a all the way through. I'm going to distribute ax squared minus 2ax plus 3a plus bx squared plus bx plus cx plus c times 1, which is c. So I used distribution in order to simplify my right-hand side. And then I'm going to collect like terms. So notice here I have an x squared and an x squared. Let's maybe throw some colors on those. I have an x squared and an x squared, which leaves me to a plus b x squared. I have an x, I have an x, I have an x. Negative 2a plus b plus c will be my x's. And let's throw up some yellow, a little 3a and a c. That's going to be my constant terms, and they are corresponding to the terms on the left-hand side. So we can see exactly what the coefficients of each side should be. And if these two polynomials are equal, then it has to be that the coefficients of x squared, the coefficients of x, and the constant terms match up on both sides. So in color, oh, I almost used the exact same right colors. Look at that. So for the x squared, a plus b x squared, that's 1x squared equals a plus b x squared. Let's just ignore the x squared. Look at the coefficients. For the coefficients of x, negative 2a plus b plus c must equal negative 4, which I forgot to put in green. Our constants, 7 equals 3a plus c. So we're equating coefficients, and that's coefficients of the various powers of our variable x. Now, in the top equation, notice, well, first of all, notice that every equation has a. And I could do a system of equations and use Gaussian elimination. I could pull out my technology, and I can let my calculator do row reduction. Or I could just give a moment to think and notice, hey, look, there's an a in everything. So in the blue equation, 1 equals a plus b, how about I solve b equals 1 minus a? And in the black equation, c equals 7 minus 3a. Because now I could substitute these into our previous equations. I don't know why that one's in green. It just threw me for a loop there for a minute. So put b into our equation, put c into our equation, and then we have an equation that's all in a. We find that a equals 2. If a equals 2, 1 minus 2 is negative 1 for b. If a equals 2, 7 minus 6 leaves a c value of 1, and I have my partial fraction decomposition. A is 2, B is negative 1, C is positive 1. Don't forget the form that we started with. That's partial fraction decomposition. Let me know if you have any questions. You will probably forget about this after a little while, but when you get to Calculus 2 and higher, you're going to want to review this. So hopefully you enjoyed it. Thanks for listening.